Okay, week 8 contents. In this week, we will use equations of motion to solve the problems of general plane motion. This will be the last week for us to study equations of motion. I will give a brief review on equations of motion, and I will show how to apply equations of motion in a problem of general plane motion. We will also learn how to deal with frictional rolling problem. Let's look at the applications. And here, the first application. This is the soil compact. When this soil compact is working, the two wheels, the front one is actually a front roller. This roller and the wheel, both of them are undergoing general plane motion. So this means both translation and rotation will be involved. One question is, when we do a design, how to determine the parameters of the pin of this roller, front roller. We can adopt rigid body kinetics to find the loading on the pin when this front roller is working. Especially when this roller is working on rough surface, you can expect the loading is much higher than that when the roller is in static. Why? Still because of acceleration. Now watch a video. Okay, front roller. A pin. On rough surface, and here shows the diagrams. This one, free body diagram, reaction force from the ground, friction force, its direction can be determined using the method we introduced before. At its pinpoint, and here is also the mass center point of this front roller, point G. We have reaction force and weight force. And in this kinetic diagram, we have MAG and IG alpha. The second application. In this one here, you can see a dummy used in vehicle crash test. This dummy is for simulating the motion of a driver or passenger undergoing general plan motion during crash. And this can be used for design the seat belt system. And we can use the analysis results to design the seat belt system. Now watch the video to see the motion of a dummy in a crash test. Okay, look at here. Not only translation, but also rotation. So this is the general plan motion. A general plan motion. Another one, we can see how different between a belted passenger and a non-belted passenger.
It's a habit for most of us to buckle up while we're driving. But what about when we ride in the rear seat of someone else's car or use Uber or Lyft? The Institute survey found that full-time belt use is lower in the rear seat, and that's especially true for people who primarily get around by taxi or ride-hailing service. Less than 60% of people who said they frequently take taxis or use ride-hailing services said they always wear their belt. People who reported buckling up less often were asked for their reasons. A quarter of respondents said they believe the rear seat is safer, so using a belt there is unnecessary. If you're not belted in the rear, you're putting yourself at risk, and you're also putting other people in the vehicle at risk. People belted in the front seat can be injured or killed by unbelted occupants in the rear flying forward in a crash. We recently conducted a test to show what can happen when there's a crash and the person in the back is unbuckled. In a simulated 35-mile-per-hour impact, the unbelted dummy slams into the back of the driver's seat, pushing the driver dummy into the deploying airbag and steering wheel. Drivers are twice as likely to be killed in crashes when the occupant behind them is unrestrained. All but one state requires adult front seat occupants to use safety belts, but rear seat passengers are covered by laws in only 29 states and DC. Only 20 have primary enforcement, which means a police officer can stop the motorist for the seatbelt violation alone. Stronger laws would help, but technology could also boost belt use. Studies show that persistent belt reminders are effective at getting front seat occupants to buckle up. These systems are common for the front seat of new vehicles, but few vehicles sold in the US have belt reminder systems for the rear seat. Although safety belts are proven to save lives, More than half of the people who die in passenger vehicle crashes in the US are unbelted.
So always make yourself belted in a vehicle. Okay, we go back to the series. And here you can see the general expression of the equations of motion. And we know there are two components. One is translational component, and this is the expression. And actually, this is the second law of Newton. Another one is rotational component here. On the left side, that's resultant moment generated by all external forces and couple moments about point P, selected point. On the right side, this is called kinetic moment. And here, the free body diagram and the kinetic diagram. These two equations are in vector form. But in practice, when we do our calculation using equations of motion, we normally do scalar calculation. And because we are studying planar kinetics, so this means our problems are 2D. So for translational component, we have two components. One is along x direction and another one is along y direction if we use an x, y coordinate system. And this one is rotational component. This rotational component, its calculation can be about the mass center point G of this rigid body, but it can also be about a point P if this point can give you convenience. For a general plane motion problem, we apply kinetic equations of motion. If we use x, y coordinate system, and here we have a free body diagram, and here we have all external forces F1, 2, 3, 4, and the two couple moments M1, 2. And here there's the weight force. And this one, kinetic diagram. And we can select point G to calculate the rotational component. We also can select a point P for our calculation. If we only look at these equations, it seems as similar as before. When we deal with the problem of translation or a problem of rotation about a fixed axis. But actually, to deal with the problems of general plane motion can be more difficult than those of translation or rotation about a fixed axis. Why? You know, in the problems of translation, the angular acceleration alpha of the rigid body must be 0. In the problems of rotation about a fixed axis, we know the relationship between the angular acceleration alpha of the rigid body and the acceleration of the mass center point g, ag, of that rigid body. They can be easily obtained. But in the problems of general plane motion, the relationship between angular acceleration alpha of a rigid body and the acceleration of mass center point g, ag, this relationship may not be easily obtained in many cases. So this means in a lot of problems, you have to do acceleration analysis. And you know, acceleration analysis is not so much easy. It will cost you time. So that's why the problems of general plane motion are more difficult than those of translation or rotation about a fixed axis. Sometimes it can be much more difficult. Let's have a brief review. Firstly, translation. We studied this in week 6. For translation, for this rigid body, you know, the angular acceleration alpha must be 0. So if we use mass center point g to calculate the kinetic moment, it must be 0. And this is in x, y coordinate system. If the problem is a curvilinear translation, it may be more convenient to use normal tangential coordinate system. And here, if we use mass center point g to calculate the rotation component, it must be 0 because alpha in translation is 0. Secondly, rotation about a fixed axis. If the problem is rotation about a fixed axis, for example here, rotation center is point O, mass center here is point G, we can easily determine the relationship between AG and alpha. And here, this is the tangential component of AG expressed using alpha, and here the normal component of AG expressed using omega. This means AG and alpha, for these two parameters, they depend on each other. They are not independent. So actually, for these two parameters, if they are unknown, actually only one unknown. We also can use normal tangent coordinate system, and you will see same thing. The relationship between AG and omega or alpha. In a lot of problems, you can see using the rotation center O to calculate the rotational component may be more convenient than using mass center point G. If you use rotation center point O to do the calculation, you can get this. This is kinetic moment, and we can do rearrangement using parallel axis theorem. And finally, this calculation of rotational component about point O can be equal to IO MMI of the rigid body about this rotation center point O times alpha. Next, example problem. In this example, there is a uniform bar, and initially it's in the equilibrium position. If we cut code AC, then this bar will get a motion. What motion will it be? It will be general plane motion. The task here is to determine the tension force in BD and the angular acceleration of this bar at the instant immediately after AC is cut. Okay, let's see how to solve this problem. Firstly, we need to define this problem, and we should know this bar AB will be undergoing general plane motion after the code AC is cut. Probably you will think at this instant immediately after code AC is cut, AB, this bar should be undergoing a rotation about an axis through point B. Actually, it's not. Why? Because B cannot be a fixed axis through point. B will be moving. At this instant, immediately after AC is cut, at this instant, the velocity of this bar AB is 0. So this means at this instant, the bar is still in static. Its velocity is 0, but its acceleration is not 0. Now, diagram. We will use an XY coordinate system. In this free body diagram, you can see we only have two external forces. One is weight force W, acting at point G, the mass center point. Another one is tension force T, acting at point B. This one kinetic diagram. We have alpha, we have AG, And here we already know the mass of this bar is 50 kilo. We don't know alpha, angular acceleration. We don't know the tension force T. We don't know AG. This means we don't know AGX, we don't know AGY. We also don't know AB. This means ABX and ABY. Okay, now the difficulty here is the relationship between AG and alpha at this moment is unknown. This relationship can only be determined using acceleration analysis. It will be relative motion analysis. We studied in week 4 and week 5. In this diagram, we assume angular acceleration alpha is positive, so it should be counterclockwise according to this defined coordinate system. We also assume the direction of AGX and AGY positive. And we will use relative motion analysis, and you know that will be vector calculation, and we can determine the correct direction of alpha, AGX, and AGY after the relative motion analysis. We have 3 equations. The first 2 are translation component. One is along x direction. The second one is along y direction. The third equation is about rotation component. This calculation may be about the mass center point G, and probably you can use point B for this calculation. MMI of this bar about its mass center point G can be calculated using the established equation. This can be found from the equation page. Along x direction, external force 0. So this means we can easily determine AGX must be 0. Along y direction, we have 2 external forces. One is tension force T, and another one is weight force W. Tension force T, we don't know. And here, we don't know. It's upward. It should be positive. Weight force W, downward, it must be negative. Okay, so we can get an equation. This gives us the relationship between tension force T and AGY. Now, the third equation. This is about the rotational component. We can use point G. Then this will be our third equation. T times 1.5. This is the summation of the moment. This one on the right side, kinetic moment. So this is it, will be our equation 3. We can also use point B to do this calculation. Then, in this case, this equation will be our equation 3. For these two, only one is possible. You can select a point G, or you can select a point B. It's not necessary to select both points for your calculation. Whatever, if you put equation 2 and equation 3 together, or equation 2 and equation 3 prime together, you will find you only have 2 useful equations, but 3 unknown parameters, alpha, ag, y, and t. So we can solve these 2 equations at this moment. So how to do? We must have one more equation. And this equation will give us the relationship between Ag and alpha. That will be relative motion analysis of acceleration. Okay, now we will go back to week 4. We will do relative and motion analysis on acceleration. And this is the bar. It has angular acceleration alpha at point G, AGY, AGX. At point B, ABY, and ABX. We select point G and point B, these 2 points, for our analysis. And we use a XY coordinate system. Okay, so that's the equation. On the left side, this is AG. This means AGX and AGY. AGX, in our previous calculation here, equation 1, we already got AGX. It should be 0. So AGX is 0. AGY is unknown. On the right side, we have ABX, ABY, and alpha, omega squared. Omega is 0. Based on our previous analysis, we know at this instant, velocity of this bar must be 0. So omega should be 0. Alpha, we don't know. ABY, we don't know. ABX, we don't know. So we have too many unknown parameters. But in this one here, ABY on bar AB is actually equal to ABN on code DB, because point B is the connecting point between this bar AB and the code DB. In code DB, point B will have a rotation about point D. D will be the rotation center of this point B. Okay, if you still remember what you have learned in particle dynamics, you know, at this instant, ABN, the normal component of the acceleration at point B, ABN, can be expressed using VB squared. VB is the velocity of point B at this instant divided by the distance from B to D. Because VB at this moment is 0, so this means ABN will be 0. If ABN is 0, then ABY must be 0. So in this way, we can eliminate one unknown parameter, ABY. Okay, so finally, we get this vector equation. And this vector equation can give us two scalar equations. Compare the left side and the right side. We can work out ABX is 0. And we also can work out the relationship between AGY and alpha. And this will be our equation 4. Now, we use equation 3 prime and equation 4. This one. Equation 3 prime. Then we can work out alpha. We can work out AGY. Then using equation 2, because we have already know AGY, then we can work out tension force T. And here you can see alpha is positive, so this means the assumed positive direction of alpha correct. AGY is negative, so this means in the diagram the assumed positive direction of AGY, that's wrong. It should be downward, negative, T positive. Okay, so these are the final answers of this problem. A particular type of problem, this kind of problem involves a uniform cylinder or a mass not uniformly distributed body of a circular shape, but the mass center point must coincide with the circle center. And this cylinder or a body of circular shape rolls on a rough surface, so we can assume the friction force is high enough. No slipping occurs. This problem will be like the problem of a front roller of a soil compact rolling on the ground. So that's the free body diagram. That's a kinetic diagram. Because this is a rolling without a slipping problem, so you know the contact point between this rigid body and the contact surface. The contact point must be an IC point. And we can select this IC point to calculate the rotation component in the equations of motion. And that will be the equation. Why can we get an equation like this? Okay, look at this diagram. And here, in this case, A is the contact point. This should be the IC point. If we select this point to calculate the rotational component, we have the summation of the moments about point A should be equal to Ig alpha plus MAG times D. So that's kinetic moment. Okay, because this is the rolling without slipping problem, if you still remember the conclusion we worked out in week 5, you know, at this point G, AG must be horizontal. So this means AG is actually equal to AGX. And this AG can be expressed using alpha, the angular acceleration, times D, the distance from G to A. This is actually the radius of this rigid body. So substitute this AG into this equation, then rearrangement this equation. We will get IA alpha. IA is MMI of this rigid body about this IC point A times alpha. Okay, because we can have an equation like this, so this will simplify the solution of this kind of problem. Now, one example. In this example here, we have a sprue. Its mass is 200 kilo. Its radius of gyration, kg, is 0.3 meter. The coefficient of kinetic friction between this sprue and the ground is 0.1. This sprue is rotating counterclockwise. And here, there is a coat wrapping on the inner hub of this sprue. So, you know, when this sprue has a rotation counterclockwise, it will be moving to right side. The target here is to determine the angular acceleration of this sprue and the tension force in the cable. Okay, we define this problem. We can see this sprue is undergoing general plane motion. Diagram, free body diagram. Okay, here there is a moment, couple moment M, and this couple moment is driving this sprue. At point A, there is tension force T from the code. At the mass center point G, G is also the circle center, we have weight force. At point B, the contact point between this sprue and the ground, there's reaction force MB. And here there is a friction force. This is kinetic friction force. So this means at this point there is slipping, and the direction of this friction force FB should be to left side. And this direction can be determined using the method we introduced before. Kinetic diagram. And here we have alpha, AGX, AGY. Okay, in this problem, A is the IC point because we normally assume no slipping occurs between a code when it wraps up in a hub like this. So A is the IC point. In this problem, B is not an IC point because slipping occurs at this point. But A is the contact point between the code and the inner hub. This point, no slipping. This is IC point. At point G, because G, this point, has a rectilinear translation. So at point G, AGY, it must be 0. But AGX is not 0. AGX because A is the IC point. So we have studied this in week 5 when we study rolling problem. We know AGX and alpha, their relationship can be easily determined. AGX should be equal to alpha times the distance from G to point A. This relationship is very useful because for this general plane motion problem, this will be our force equation. Now, look at the first 3 equations. This one along x direction, we have T and FB. T to right side, positive. FB to left side is negative. AGX, because we have already know the relationship between AGX and alpha, so we can express AGX using alpha times 0.4. So this means now we have already eliminated one unknown parameter, AGX. In this equation 1, we have T, MB, and alpha. In equation 2, along y direction, we have weight force W, negative, MB, unknown, but it should be positive. AGY, we know it must be 0, so from equation 2, we can work out MB easily. Then in equation 3, for rotational component, we select point G, the mass center point, to do our calculation. We have couple moment M, this one counterclockwise according to the defined coordinate system. It should be positive. We have the moment generated by T. This should be clockwise, negative. Moment generated by FB, this one clockwise, this moment clockwise, negative. On the right side, it's kinetic moment Ig alpha. We can substitute MB into this equation to work out FB. Now, using equation 1 and equation 3, we can work out alpha and T. Next, we introduce friction rolling problems. This kind of problems is about the rolling motion of wheels, cylinders, or discs. We don't know the rigid body rolls without slipping or slipping occurs when this rigid body rolling on a surface. So for example here, that's the rolling rigid body. At this contact point, we don't know if slipping occurs. We can have a free body diagram. Weight force, external force P, reaction force at this contact point, friction force. But we don't know this friction force is a static friction force or kinetic friction force. We can have 3 equations along x direction. In this equation, normally we don't know friction force F and Ag. Along y direction, we have Ng and Mg, the weight force. This one can give us N. The third equation about the rotational component, and here, if the calculation is about mass center point G, we have friction force F, we have an unknown angular acceleration alpha. Okay, now you can see we have 3 equations but 4 unknowns: F, Ag, alpha, and N. So we can't solve these 3 problems. In this case, what can we do to solve the problem? To deal with this kind of problem, we have to make assumption. So we can get one more equation for us to solve the problem. This one more equation can be obtained from the slip or non-slip condition between this rigid body and the ground. Normally, firstly, we assume no slipping occurs. Okay, now if no slipping occurs, if we know the static friction coefficient mu s, can we use this mu s times n to express the friction force, the static friction force between this rigid body and the ground? The answer is no. Why? We studied before. We know using mu s, the static friction coefficient, times n, we can only know the maximum available friction force. But we don't know the actual friction force, because the actual friction force should be less than this maximum available friction force or equal to it. But here, because of no slipping, the contact point between this rolling rigid body and the contact surface, this contact point will be the IC point. If this is the IC point, based on our study before about rolling motion, we know the relationship between Ag, the acceleration at this circle center point G, and alpha can be easily determined. So this will be our fourth equation. And then using this fourth equation combined with the 3 equations in last slide, we will be able to solve the problem. But because we made assumption before we can work out this fourth equation, after solving the problem, we must verify the assumption was correct. How to do this? We have to check the friction force F and the maximum available friction force calculated using mu s and reaction force N. If the calculated friction force is less than or equal to this mu Sn, then that means the assumption was correct. But if you find the friction force you worked out is larger than this mu s times n, the maximum available friction force, and you know this is impossible, then that means the assumption you made, the assumption of no slipping, is void. And that means in your problem, slipping must occur. If slipping occurs, then your force equation will be Ff is equal to mu k times n. Ff this time it will be kinetic friction force. If you know kinetic friction coefficient, you can use mu k times n to work out Ff. This will be your force equation. In this case, you can't use Ag is equal to alpha r because slipping occurs. Ag will not be equal to alpha r. Okay, for this static and kinetic friction force, we watched a video before. Probably you already forgot this video. Let us watch it again.
In this video, we are going to analyze how the coefficients of static and kinetic friction affect the amount of force needed to make an object move. Here we have a force sensor. As you can see, as we pull on the string that is attached to the hook on the sensor, the computer reads off how much force is being applied to the sensor. We will use this to analyze the amount of force required to move carts with different coefficients of friction.
Here we have a cart with added weight on it. This cart is attached to the force sensor through the string. As you can see, we have different carts with different surfaces on the bottom, so we can analyze the graphs of the different coefficients of friction.
So let's look at our free body diagram first. We have our weight acting down on the object, our normal force acting up on the object, and we have our force acting horizontally to one direction and our friction force acting on the opposite direction. Now, through Newton's second law, we can derive that our normal is going to be equal to our weight, so our friction force equation is going to be equal to mu times mg. Now, if we look at our first part of the graph of our friction force with respect to time, all the way up to the peak, we have our static friction, which is going to be less than or equal to our mu s times mg. And when we reach the peak, our maximum static friction is going to equal our mu s times mg. Now, this straight line afterwards refers to our kinetic friction, and this is going to be equal to our mu k times mg. Now, if we solve for mu s and mu k, we have our mu s equal to our maximum static friction over mg, and our mu k is going to be equal to our kinetic friction over mg.
Here we have our cork surface cart. The total weight of the cart is 10.78 newtons. As we pull it, we can see the amount of force generated on the graph below. Our peak force value is 5.858 newtons, so the coefficient of static friction is 0.543. The average moving force is 4.786 newtons, so the coefficient of kinetic friction is 0.444. We can do the same experiment with the felt and plastic surfaces. For the felt, the static coefficient of friction is 0.228 and the kinetic coefficient of friction is 0.208. For the plastic, the static coefficient of friction is 0.178 and the kinetic coefficient of friction is 0.127. As you can see, it requires more force to make a cart start to move than it does to keep it moving. It also depends on the surface of the cart. As the roughness of the surface increases, so do the coefficients of friction and the applied force. This allows us to conclude that the force acting on the carts is proportional to the coefficients of friction and that the coefficient of static friction is larger than the coefficient of kinetic friction.
If you don't remember the conclusion we have got in week 5 about rolling motion, you can refer back to the slides in week 5. Rolling motion, if rolling without a slip, and you know the velocity at the circle center point G can be expressed using omega and the radius of this disk or cylinder. And the acceleration at point G can be expressed using angular acceleration alpha times the radius r, and at its contact point A is the IC point. At this point, AAX must be 0, but AAY can be expressed using omega squared times the radius. And here, just a brief review how to determine the direction of friction force in rolling motion. Firstly, we assume no friction and observe the resulting motion. In second step, the friction force must always act on the body opposing the motion of the body. So here, for this front wheel is the driving wheel. The direction of the friction force should be to left side. But for the rear wheel, this is the driving wheel. The direction of friction force must be to right side. There is a complicated case about the direction of friction force in rolling problem. The problem will be like this. And in this one here, you can see sometimes the direction of this friction force at the contact surface is to right side, and sometimes is to left side. Why? This is because of the position of the acting point of this point P. When the acting point of this external force P is far away from this circle center, the friction force direction will be to right side. But if this acting point of this external force P is very much close to the circle center G, then the friction force F its direction will be to left side. If the distance from this acting point of the external force P to the circle center point G, this distance R is equal to I over mr. I is the mass moment of inertia of this sprue about point G. M is its mass. R is the radius of this sprue. In this case, this sprue even can roll without slipping on the frictionless horizontal surface. This is a very special case. Okay, a new problem. In this problem here, we have a uniform rod, slant rod. Its mass is 100 kilo. Its MMI about its mass center point G is known. The mass center point should be the middle point. Between this rod and the ground, at this contact point, there must be friction force. And here, we already know the static friction coefficient is 0.3. And we also know the kinetic friction coefficient is 0.25. At this point, there is an external force. This force is horizontal. It's 400 Newton. The distance from this acting point to the contact point A is 0.5 meter. The task here is to determine the rod's angular acceleration at the instant when this external force is applied. Initially, this rod is at rest. Before we can solve this problem, we need analysis. What will happen if an external force acting at this point? Actually, there will be two possibilities. The first possibility, when the friction force between this rod and the ground is very high, you have an external force applied at this point. What may happen? This bottom end of this rod does not move, and this rod will be falling down. So this means point A becomes a fixed axis through point. This rod will be undergoing a rotation about this fixed axis through point. In this case, the friction force at point A should be static friction force. And this friction force should be less than or equal mu s times Na. Na is the reaction force at this point A. The second possibility is if the friction force between this road and the ground is not very high, when we apply an external force here, the bottom end of this road will be moving. In the meantime, because this is a slant road, it will be falling down. Then in this case, this road will be undergoing a general plane motion. And at this point, point A, the friction force will be kinetic friction force. It can be calculated using mu k times Na. Okay, this problem is not a rolling problem. But because of the existence of these two possibilities, the methodology of solving this problem will be as same as that for a frictional rolling problem we introduced in previous slides. And here, an assumption is needed. Based on our analysis, we can define this problem. Two possibilities. Possibility 1, rotation about a fixed axis through point A, the end point. Possibility 2, general plane motion. So firstly, we can assume no slipping at point A. That will be possibility 1. Okay, then we can solve this problem. It will be a problem of rotation about a fixed axis. We can get a result. But because we made an assumption here, we must verify this assumption. If we find the assumption is void, then that means this possibility 1 is impossible. Possibility 2 must be true. Then we will need to do calculation based on possibility 2. That will be a problem of general plane motion. Okay, next, we will solve this problem by assuming possibility 1, a problem of rotation about a fixed axis through point A. Here is free body diagram, and here we have weight force W, external force P. At this end point A, we have reaction force Na and friction force F. It's not difficult to determine the direction of this friction force F should be to left side. But F at this moment is unknown, so I can assume it's positive according to this defined coordinate system. This will be easy for dealing with the sign of an unknown parameter. But if you don't like, it's not necessary for you to assume this direction of friction force positive. Kinetic diagram. M, AGX, M, AGY, and alpha. Please note, now this is the problem of rotation about a fixed axis through point A. So this means AGX and alpha, they are not independent. Why? You can see A is the rotation center. At this instant, this rod is vertical in its vertical position. So here, this AGX is actually equal to AGT, the tangential component of AG. And AGY is actually equal to AGN, the normal component of AG. So this means AGX should be equal to AGT and equal to alpha times the distance from G to A. In this diagram, we can assume alpha positive counterclockwise according to this coordinate system. Then AGT, this direction, must be to left side. Okay, we know MMI about point G of this slender rod. We know its mass, external force P, mu S, mu K, and omega, the velocity at this instant must be 0. Equations. The first two, translation the component along x direction, along y direction. Rotational component, the calculation can be about the mass center point G, can be about the end point A. Along x direction, we have friction force F, P, external force. AGX, we have expressed AGX using alpha. In the diagram, you can see AGX to left side. So here, I should give a negative sign. This negative sign is for AGX, but not for alpha. So we have equation 1. Along y direction, we have weight force W and reaction force NA. AGY at this instant, there must be 0. Why? As mentioned just now, at this instant, because the road is vertical, so AGY is actually equal to AGN. And we know in a problem of rotation about a fixed axis through point, AGN can be calculated using omega squared times the distance from G to A. And omega is 0, so AGY should be 0. So this equation will give us NA directly. Rotational component. Here, I use mass center point to do the calculation, and I can establish my equation 3. So using equation 1 and equation 3, we can work out friction force F. It should be negative 300 Newton, and alpha should be negative 0.667 radians per second squared. So this means the assumed positive direction of friction force is wrong. It should be negative to left side. And also the assumed direction of angular acceleration alpha should be negative instead of assumed positive. Now we will check the assumption. The maximum available static friction force at the endpoint A can be calculated using mu s times NA. So this will be 294 Newton. Compare this maximum available friction force and the friction force we worked out from our calculation. You can see this maximum available friction force is less than the friction force we worked out. This isn't possible. So this means the assumption of no slipping at point A is void. And this means the assumption of a rotation about a fixed axis through the endpoint A is void. So slipping must occur at point A. Then that means at the endpoint A, the friction force must be kinetic friction force. It can be calculated using mu k times NA. By observation, it's easy to know the direction of this friction force should be to left side. Okay, now we know this is not a problem of rotation about a fixed axis through point A. So this means the relationship between AGX and alpha does not exist. This is the problem of general plane motion. Now we have to do recalculation. Now we redraw the free body diagram and the kinetic diagram. We still use this xy coordinate system. In this free body diagram, weight force, external force, reaction force at point A, and kinetic friction force F. In this kinetic diagram, we still assume this angular acceleration alpha counterclockwise positive. Now, we can't easily relate AGX to alpha. We just assume both unknown AGX and AGY are positive. For AGY, again, because at this instant, this road is vertical. So at this instant, the velocities at any points in this slant road must be horizontal. So that means an IC point must be somewhere along the vertical line going through point G. We don't need to know the location of this IC point. And we can calculate AGY using VG squared divided by the distance from G to this IC. Because at this instant, the slant road is at rest, still at rest, so VG must be 0. So that means AGY will be 0. Okay, we can still have the 3 equations along x direction. We express the kinetic friction force using reaction force NA, external force P, 400 Newton, 100 times AGX. AGX is unknown. Along y direction, as same as before, we can work out NA directly. Rotational component, we can establish our equation 3. And in this equation, we have NA and alpha, 2 unknown parameters. Okay, substitute NA into this equation 3, we can work out alpha. And substitute NA into equation 1, we can work out AGX. This will be the final answer to this problem. For a friction rolling problem, we will have a tutorial problem, and that problem is the friction rolling problem. And you will see the solution will be as similar as this. We need assumption in the very beginning, and then we must verify this assumption